Welcome everybody. I hope you got a chance to see the videos of previous sessions. Generally, I want to encourage again people to ask questions. It's helpful not just for you but also for me. And I think what will generally happen is I will post a link to the updated notes here in the chat, so you could follow pretty much an updated version every time. All right, so without further ado, let's start by recalling what we had last time. Is that yes? Yeah. So to ask a question, just raise a hand, and I can hear the ping, and I will stop and then give time for it. So before I start, maybe any questions about previous materials?
I have one related to the previous exercise that you left, which was related to using Fermat's theorem.
Yeah.
So I spoke with Rafael, who was very kind and kind of showed me the proof on where the 2 was appearing from the wild. But it's true that you started talking about binomials to actually justify your proof where the 2 from the equation was appearing from. So I'm a bit curious if you could give kind of the solution for the exercise that you sent in the session.
Okay, let me try to repeat it. Not with the binomials. I will get to the binomials soon.
Okay, sure.
So suppose you have actually I'll choose K here. Is a field of a characteristic P. This means, I remind you, that 1K plus itself P times is equal to 0, or to 0K. And what we showed is that within K, you have let's call it F. I take 0, then 1K, then I will denote as 2K, simply 1K plus itself. And this goes on until what you can denote as P minus 1 sub K, which is, right, it's just 1K plus itself. P minus 1 times. And I claim that, of course, this is a subset of K. It contains the 0 element and the unit element. It contains an additive inverse for every element, because the additive inverse for minus a sub k is simply p minus a sub k. Okay, of course, this if you add these two together, you get p sub k, and p sub k, this is p sub k, is 0, because we are in characteristic p. So you have an additive inverse, and now, I mean, so this, if a is a number between 0 and p minus 1, then you have an additive inverse to a sub k, but also you know that in fp, you have a multiplicative inverse for a. I mean, there exists u in fp such that a times u is equal to 1 mod p, which is equivalent to say that there exists some v, again, between 0 and p minus 1, such that au plus pv is equal to 1. But then you can add sub k to this equation, right? I mean, what is a in fp? A in fp is simply 1 plus 1 a times, and the same for u, p, and v. So what I can deduce is that a sub k times u sub k plus p sub k times v sub k is equal to 1 sub k. But p sub k, this is what is written here. P sub k is 0. So what I get is that I have a multiplicative inverse to a sub k. Right? There exists u such that a times u is equal to 1. This, of course, here I need that a would be different than 0. So is this clear?
Yep.
Okay, so what I get is that this f is a subfield of k. It's a subset containing 0 and 1. If you wish, I mean, of course it's closed under addition, it's closed under multiplication, and it contains the inverses of I mean, the additive inverse and the multiplicative inverse. So f is a subfield of k. Now, as you can see from this reasoning about the multiplicative inverse, the elements, I mean, the operations in F behave exactly like the ones in FP. I mean, the only thing is that I have to formally add this subscript k, because it's not like real natural numbers. It's kind of adding the unit element of k to itself this many times. So of course I can construct an isomorphism from F to FP. If you wish, you can construct in this direction. You send 1k to 1, and ak again you send to a. And this respects, this is a homomorphism because it respects addition and multiplication, and it's clearly a one-to-one map, because I mean I have exactly the same number of elements in each side, and I'm doing a one-to-one correspondence. So in fact, this is an isomorphism of fields. And the corollary of all this is that a field of characteristic P contains an isomorphic copy of FP. Is this clear? Okay, so but observe that K, if K is a field of characteristic P, it is in particular a abelian group with respect to addition. I mean, K plus 0 is an abelian group. And in abelian groups, we also have for any integer, actually, we defined and any, let me call it V in K, we defined A times V to be V plus V A times. Where if A is negative, you take minus V plus itself A times. Okay? So now potentially we have a conflicting notation. It's not exactly conflicting. If we pay attention, we could write AKV, right? Because AK is an element in K. So I could multiply AK by V via the multiplication of elements in K. And so what do you make of it? I have two things that look the same, but are they the same? So I could write this expression as 1k times V plus itself A times. And by the distributive axiom of fields, I am allowed to write it as 1k plus itself a times v. And this, of course, by definition, this is our a sub k times v. So you see the two notations coincide. Now, what I can do in this situation is I have this. I mean, for any A and B in FP, I can do, and for any V in K, I can do A plus B in FP and then multiply it by V. And this will be equal to A times V plus B times V. I should say, I guess, from this equality, what you can deduce is that if you take P and you multiply it by V, well, I mean, you get PK multiplied by V, and PK is 0. So you get 0 times V, which is 0. And this is why this equation star holds if I interpret, let me write it explicitly, if I do A plus, but plus in FP with B, then it's the same as doing A times V plus B times V. Now, in addition, I have A times V plus W equals AV plus AW. And this is for any A in FP and VW in K. Okay? And what I claim is that this kind of structure, let me put 2 stars here. So these essentially these two conditions, star and double star, are useful to abstract in order to understand the structure of fields of characteristic P. This should motivate the following definition. Yeah. So let F be a field. A vector space over F is a set V with a specified element zero V, and well, binary operations. I have actually two. So one binary operation is plus. This goes from the Cartesian product of V with itself to V. So it means you can take two vectors and add them together. Like you have V plus W. And the other operation is called multiplication by a scalar. This takes an element in the field and an element in V, and gives you back an element in V. So you can imagine that. I mean, here I take V comma W, and the notation would be V plus W. And here I take A comma V, and I send it to A times V. Okay, so this is the data of a vector space, but as usual in these kind of algebraic definitions, we want some conditions that this data satisfies, and the conditions are pretty easy or pretty intuitive in light of the discussion. So one, I want that V with this addition and the zero element, 0V, is an abelian group. And then I have one condition is that I want associativity of this. This is called multiplication by scalar. And this is called addition of vectors. So I want the multiplication by a scalar will be associative. This means that for any A, B in F, and for any V in V, A times BV is equal to A times B times V. You see here, the multiplication is the multiplication of F. Okay, so this is associativity of multiplication by a scalar, and the third axiom is compatibility between addition of vectors and multiplication by a scalar. Namely, we want distributivity. So for any A in F, or let's say for any A, B in F, and VW in V, I can do two things, right? I can do first A plus B times V, and this should be equal to AV plus BV. And I can also do A times V plus W, and this should be equal to AV plus AW. Okay, so this is a vector space. And the main example for us for a field K with characteristic P, K is a vector space over FP. Any questions about this? Of course, this is a new notion, but I hope it's more intuitive now that we had definitions of similar algebraic structures. Now, let me get back to your question, Carlos. You asked about this binomial argument.
Sure.
So for a field K with a characteristic P, for any X and Y in K, I claim this is the sometimes referred to as the freshman lemma. This is what we discussed in FP, which means that X plus Y to the P is actually X to the P times Y to the P. Like the very naive equation actually holds. And the reason, I mean, we actually, if you remember when we proved we took X plus Y to the P and we decomposed it via the binomial formula. So this is sum of P over I, X to the I, Y to the P minus I. I equals 0 up to P. And we noticed that if I is strictly bigger than 0 and strictly smaller than P, you take P over I is like P factorial divided by I factorial times P minus I factorial. But since P is prime, actually, P divides this expression. So you could write this P over I as P times something, let's say T. But then, as we saw in the discussion at the beginning of the session, when you multiply by P, you get 0 in characteristic P. So all these expressions in the middle vanish, and you get that Ex plus Y to to the p is equal to x to the p plus y to the p. Okay, so this is the sketch of the argument. You could take it as an exercise to go over the proof of this this lemma. This lemma was stated in FP. Previously, we proved it in FP, but in fact, it's true for any field of characteristic P. Okay. So this and if you want, moreover, x plus y to the p to the n is equal to x to the p to the n plus y to the p to the n. Well, how do you do it? You do induction. I mean, it's really trivial induction. For n equals 1, we know it. And for n equals 2, well, I'll leave it to you.
Okay.
Okay. So, okay. So this is an aside, but what we really care about, because we want to understand general fields of characteristic P, and this structure of a vector space over FP is the first stepping stone into classifying fields of characteristic P. And what we really need to do about the structure of vector space is again to classify vector spaces, more specifically what is called finitely generated vector spaces. But we'll get to that. So the plan for this session and probably the next one is to classify finitely generated vector spaces, which I will explain in a minute, and use it in order to get a first stepping stone into classifying fields of characteristic P. Any questions? Okay, so famous vector spaces. Well, of course, every field F is a vector space over itself. Right? I mean, of course, you can take A in F and V in F, and you can do A times V, and it will satisfy all the axioms. More generally, you can take the Cartesian product. This is written as F to the N. So you take F Cartesian product with itself, N times. And I remind you, the Cartesian product is the set of all tuples, say x1 up to xn, such that for any I, xi is in F. Now, on this Cartesian product, you have the structure of a vector space by defining a scalar multiplication by A let's say V is x1 up to xn. Then I define A. Well, let's maybe first do addition. So if W is y1 up to yn, you simply do addition in F in each coordinate. So this is x1 plus y1 up to xn plus yn. And for a scalar A, you do AV as simply AX1 up to AXN. Okay? And of course, the zero vector, 0 Fn, is the vector with all the coordinates being the zero element in F. So, okay, I mean, the Cartesian product, since F is F with the zero element in addition is an abelian group, we saw that if you take the Cartesian product of abelian groups, or even just generally groups, you get another group with exactly with this operation. So clearly, Fn is abelian group with respect to this this addition operation, and multiplication by scalar is associative because we do it in each coordinate, and in each coordinate you do multiplication in F, and multiplication in F is associative. So you get associativity of a scalar multiplication, and also distributivity. Since I do it in each coordinate, I actually have distributivity because I have distributivity of in F, so in each coordinate. Okay. Now, the kind of the general principle from the discussion we had in the beginning of the session is that if you have any field inclusion, this is a subfield inclusion, then K is a vector space over F. So, for example, R is a vector space over Q, and C is a vector space over R, but also C is a vector space over Q, because Q is also a subfield of C. As a non-example, R is not a vector space over FP. Even though you could of course, you could think of the element in FP as included in R, right? It's just the integers 0 up to p minus 1. But the operations in FP are not compatible with the operations in R. So when you will try to do, let's say, you take A in FP and V in R, Let's say you take two elements, you take A and B in FP. Then you may do A plus B in FP and then try to multiply it, but this is not going to be equal to take A multiplied by V plus B multiplied by V, because here the multiplication is meant in FP. So for example, if I take A to be 1 and B to be P minus 1, then A plus B is 0. So multiplied by V is going to be 0 always, but A times V is V, and B times V is P minus 1 plus, P minus 1 times V. So I get P times V, which is not equal to 0 in R. Yeah.
It's like a naive question, but we don't have a requirement for vector space elements to be vectors. They are still like field elements.
For us, vectors is just a terminology for an element in a vector space.
Okay.
Okay, so this is unlike because we take kind of an abstract approach. Of course, what you usually learn in like preliminary mathematical courses is that you take, for example, the plane. The plane is simply R2. R2 is the Cartesian product of R with itself. Right? And then you take like an arrow that starts from the origin, and you call it a vector, right? But this, in our language, we simply refer to this point. This V is going to be some point in the, the end point of V is going to be x comma y. And for us, this is the vector. It's simply an element in R2. And of course, if the field we are working over has kind of geometry, then we can interpret vectors in a geometric way. But we are really interested in fields of characteristic P. And these guys, they don't really have any apparent geometry. So we really need to take this abstract approach and anyway, this is the kind of origin of the terminology, is this geometric meaning. So it's good to keep in mind. Is this answer your question?
Yeah, sure. Thank you.
Okay. Maybe a less trivial example, because we want to do kind of a bit more abstract stuff. take the field with two elements. So I take F to be F2. And consider the power set. Let's say I take the field of two elements and X, an arbitrary set. The power set of X is the set of all subsets of X. This is the set of all S such that S is a subset of X. Of course, including X itself is a subset of X, and also the empty set is a subset of X. Now, we take V to be simply this power set, P of X. And now I need to tell you how to add two vectors and how to multiply by a scalar. So actually, let's first start with the multiplication by a scalar. I mean, of course, 0 times S should be 0. I mean, the 0 element of V is the empty set, right? It's a subset of X, so it's an element in V. Then multiplication by a scalar, I really have no choice because 0 times any vector needs to be 0. So 0 times S is going to be 0V, which is the empty set. And 1 times S, again, I don't have any choice because 1 times any vector in a vector space is the vector itself. So it's S. This maybe you can do as an exercise. It follows immediately from the axioms of a vector space that if you take the unit element of the field, in this case 1, you multiply it by a vector, by any vector, you get the same vector. Okay, so this, let's put it like this, exercise true in any vector space. Okay, so multiplication by a scalar is kind of canonical. Now I need to tell you how to add two vectors and what is the additive inverse. So for two vectors, S and S prime in V, this really means S and S prime are subsets of X. I define the addition to be the so-called symmetric sum. So I take all the elements in S that are not in S prime, union all the elements in S prime that are not in S. And minus S is defined to be the set of all elements in X that are not in S. Okay, and you can do this exercise and verify But this is indeed. Okay. Any questions about this?